Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we're looking at a pretty monumental shift in technology. For the past couple of years, we've all been completely fascinated by AI that talks, right? Chatbots that can write essays, draft emails, brainstorm ideas with us. But the era of AI simply talking, that's kind of coming to an end. We're now entering the age of AI that acts. We're moving away from passive conversationalists and towards dynamic systems built to navigate the real world. And honestly, the architecture powering them is nothing short of fascinating.
Now, I want you to just hold on to this question as we go through the material today. What actually happens when an AI system is given the keys to the car? When it stops waiting for you to hit enter on every single prompt and instead just starts making decisions, executing commands, and navigating obstacles completely on its own? That right there is the fundamental transition from standard generative AI to what we call agentic AI.
Okay, let's dive right into this. At its core, an AI agent, which is sometimes called a compound AI system, is essentially a goal-directed entity. Instead of just trying to predict the next word in a sentence, an agent is given a human-defined objective. And it can actually break that objective down into multi-step tasks, grab external software tools to gather information, and take autonomous actions to reach the finish line. Its brain, its control flow, is driven by large language models, sure, but it is fundamentally built to execute a workflow. Here is our structural roadmap for the explainer today. We're going to cover 1. Real-world applications and risks. 2. The AI hardware bottleneck. 3. The tri-spirit architecture. 4. Building AI muscle memory. And 5. The future of efficient AI. All right, Section 1. Real-world applications and risks. So let's ground this in reality for a second. Where are these AI agents actually operating right now? Because they aren't just theoretical lab experiments anymore. They are already being deployed out there across critical sectors. The United States Internal Revenue Service, for example, is using agentic AI for taxpayer advocate services. Over in the UK, Staffordshire Police announced trials to use agents to handle non-emergency 101 calls starting in 2026. In software development, you've got tools like Cursor and Claude Code actively writing and debugging code autonomously. We're seeing web browser agents that click around and navigate sites for you, and we're even seeing them deployed in video game development and crypto trading. I mean, they're literally everywhere. But, as you might guess, handing over autonomy introduces some pretty severe systemic risks. The source material outlines something called agentic misalignment, which is basically when the AI strategies diverge completely from what the designer actually intended. We're looking at risks of agents getting stuck in infinite loops or compounding software errors. Security is obviously a massive concern, requiring advanced cybersecurity threat modeling frameworks just to wrap our heads around the vulnerabilities. And looking impartially at the data, the environmental impact is staggering. According to NVIDIA's CEO, AI agents require up to 100 times more computing power than standard language models. 100 times. That energy cost is a monumental red flag. Which brings us to Section 2, the AI hardware bottleneck. And this right here is the core conflict of our entire explainer. Our current hardware paradigms, they are simply not built to handle the intense, conflicting demands of these autonomous agents. Right now, we're stuck between two flawed extremes. On one side, the cloud-centric model gives you massive intelligence, but sending data back and forth to a server introduces a 1 to 3 second delay. I mean, think about an AI agent driving a car. A 3-second delay before deciding to hit the brakes is an eternity you really don't want to experience. Plus, it drains energy and completely dies if you lose your internet connection. On the flip side, we have edge only. This means running the AI directly on your phone or device. It's lightning fast and private, sure, but the intelligence is severely handicapped by the physical size of your device's battery and processor. Neither of these can realistically support the future of AI agents on their own. Let's move on to Section 3, the tri-spirit architecture. Now, what's really interesting about this slide is how it solves the bottleneck. Researchers in a recently published archive paper have proposed a revolutionary structural solution. Instead of trying to shove all of an AI's brain into the cloud or squeezing all of it onto a phone, the tri-spirit architecture fundamentally changes the approach. It explicitly decomposes intelligence into 3 distinct, specialized layers that communicate back and forth through an asynchronous message bus. You can actually think of this a lot like human cognition. So layer 1 is the super layer. This lives up in the cloud. It operates on a slower timescale of seconds to minutes, handling long-term episodic memory and massive, complex planning.
Down from that, layer 2 is the agent layer. This one lives right on your device using a more compact language model. It handles active reasoning and task breakdown much faster. We're talking milliseconds. And then layer 3 is the reflex layer. This operates in lightning-fast microseconds. It handles direct sensor execution with absolutely zero active language model thinking. Just like you and I have deep planning cognition, what psychologists call System 2, and immediate automatic reflexes, System 1, this architecture gives AI the exact same physical structure. Okay, on to Section 4, building AI muscle memory. But how does a system actually learn to use that microsecond reflex layer? Well, let's see how this builds upon the layers we just talked about. Say you ask your AI agent to perform the exact same task every single morning, like turning on a specific set of lights and summarizing your calendar. The agent layer notices this repetition. It detects that high-frequency pattern, and instead of using valuable reasoning power to think about this task from scratch every single day, it abstracts that sequence and compiles it into a direct trigger. It pushes that learned behavior all the way down to the reflex layer. So the crucial point here is that the AI builds literal muscle memory. It converts those heavy, power-hungry reasoning traces into lightweight, stateless execution policies. So the next time you ask for that morning routine, the reflex layer executes it instantly, in microseconds, bypassing the language model completely. It costs absolutely zero energy and requires zero thinking. Pretty amazing, right? Finally, Section 5, the future of efficient AI. So what happens when we zoom back out and actually run this 3-layer architecture through rigorous simulations? The numbers here are just incredibly compelling. When compared directly against a traditional cloud-centric AI model, the Tri-Spirit architecture achieved a massive 75.6% reduction in mean task latency. That is literally the difference between an AI pausing to think and an AI acting instantly in the real world. But it didn't just get faster. Remember that massive 100x compute bottleneck we discussed at the beginning of the explainer? Well, the simulation showed a 71.1% reduction in total energy consumption. By routing simple tasks right to the device and compiling habits down to the reflex layer, the system stops wasting massive server power on basic actions. This is a monumental revelation for the environmental sustainability of AI. And this brilliantly illustrates the incredible balance the whole system achieves. Look at this. The traditional cloud-centric model lags way behind at over 2,000 milliseconds of latency. The edge-only model is incredibly fast at just 179 milliseconds, but remember, it entirely lacks the capacity for any deep reasoning. Tri-Spirit threads the needle perfectly here at 523 milliseconds. It achieves near edge-level execution speeds for routine tasks without sacrificing the cloud-level reasoning you need for complex goals. So, to bring all this amazing source material together, the definitive takeaway is this. Cognitive decomposition, actually splitting the brain into specialized parts, is drastically more efficient than simply building bigger and bigger models. Tri-Spirit requires 30% fewer LLM invocations per task, and unbelievably, it guarantees a 77.6% offline task completability rate. That means if your internet suddenly cuts out, your agent doesn't just freeze up. It keeps executing local and reflex tasks seamlessly. This is exactly how we build a safer, faster, and much more energy-efficient foundation for the real-world deployment of autonomous AI. We started this journey with basic chatbots, and we are rapidly moving toward agents with microsecond reflexes and perfectly compiled muscle memory. The technology is breaking through these massive hardware bottlenecks right before our eyes. So I guess the only question left is the one we started with. Are we ready for an AI that doesn't just think for us, but acts on our behalf with zero hesitation? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll see you next time.